Okay, so the genesis of this was that Josh and I were talking last night, and just talking about LX stuff. And he had mentioned it'd be great to actually have a little more information on how to debug LX problems when they go south. So I thought it would be useful to informally share what we know. A lot of this is stuff that actually reflects incomplete work. That once we fix bugs, it will invalidate some of this. But so this is basically showing you how to debug right now, but some of that will change. And the genesis of this was that we had a core dump in particular, a core dump, and I'll show you what that looked like. Make sure that I'm not actually running the D script that will solve the problem. No, I'm not. So we had a core dump when running bash. So if I log in to, I'm in this Nginx container and fine. And if I run bash, segmentation fault core dump, right? This is like the classic LX branded zones are not working. So all right, now what? And there are a couple of things to start with before, just for whatever it's worth, before I actually go into just looking at the core dump, because core dumps can be tough with LX for a variety of reasons. If you've got something that's totally reproducible, it's the first thing I do, even though I think Jerry winces a little bit because he hates this and wanted to rip it out, but I actually find it useful, is I set LX debug. Jerry, I think Jerry likes it more now that I've turned them into dtrace probes. I think that Jerry's workflow is just a little bit different. I think he's fine with it now. But if I run LX debug, that is going to give me output whenever, and this is more useful to us than probably. I mean, getting syscall output, strace output is useful. Truss output is somewhat useful. This is a little more.
That goes to standard error or standard?
That goes to standard error, I believe. But this can also be extremely. Oh, there you are. Enable to path dev to DY. You can actually change the path that goes to. This can also be really annoying when you're getting way too much output.
Yeah.
So the other thing you can do, if especially if you've got something kind of complicated going on the screen, and you want to get this output but somewhere else, is you can actually set. I made dtrace probes that correspond to these things, and so this is on the head node here. If I set by default, if I do a dtrace minus L minus P LX star, I am only seeing the LX syscall probes. I'm not seeing any of the LX PID provided probes. And so in particular, if I look for debug, I won't find anything. If I set LX dtrace to be 1 and then run something, that will create dtrace probes that correspond to those LX debug points. So now if I look for this, I'll see the debug probes. So what that allows me to do is I can, and this is actually really useful for debugging init problems as well, where you don't necessarily have the ability to get LX debug output over a console because other things are busted, is to either set LX debug to 1, and I'll show you another way to do it, where if you can't even inject into the environment, or it's painful to inject into the environment. And that allows you to get dtrace probes that now correspond to LX debug output. So if I just do printf %s copy instr arg0 minus q minus x size equals whatever 4k. So now if I run something, I will see that same LX debug output. If so, I'm going to exit that. You'll note if you just run that and it doesn't find any probes because you haven't yet run the thing that you want to instrument, that will fail because it doesn't find any probes. You can tack on -Z, and it will say, okay, like I don't match any probes, but I guess I'll just hang out waiting for probes to materialize. And now if I do LX dtrace equals 1 and run bash, I'll see segmentation file core dumped, but now I've got much more interesting data. So this is all helpful. In this case, it's not hugely helpful because in this case we don't actually see. And actually, one thing that is kind of interesting that you would have to be you always have to know what the root cause is to actually really see. Normally, when we take a signal, you see things like this. Let's see where we took a signal. Interpose Catalumo signal 11, that's 6XV, translate the Linux signal 11, da, 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 da. And we're not seeing any of that. We're not seeing the fact that we caught a signal 11, which indicates that there might be some problem with the signal handling. But so anyway, that is just some quick stuff for using dtrace and LX debug. And the reason it's not on all the time is because it actually does have effect, especially when you're creating and spawning a bunch of processes. We actually don't want to be creating these USDT providers for really light processes. So that's the reason you have to set LX dtrace to 1. You do.
So like I said last time, I think you should be able to set that
cool. Right.
Docker run. So if you do Docker run -d.
Let's do that.
It should work, I think.
Cool. Yeah, let's do that. So does exec take a -d as well, or only run?
Exec is, I don't remember actually.
And so,
No,
thank you, Docker. It's totally lame.
Well,
anyway, so fine. That should work then. I mean, if
we wanted to make the exec just do that by default,
I wouldn't. I mean, I think that this is only. Like I said, it does have disabled probe effect, and hopefully we won't be debugging these kinds of problems forever. So, and these problems, at least for right now, are still kind of the reproducible variety. This also, by having dtrace probes, it also allows you to do things where you are string matching on things that are interesting, and then using the stop action to stop a process, and then you can attach the debugger to it and make better sense of it. But in this case, so let's just run through it again with this case where we ran bash, we got a core dump, so let's hop over to the core dump and actually look at that. So we never take a Linux core dump. The core dumps are always native core dumps. So when an LX branded zone process dumps core, it is always and it always will be a native core dump. So those two things differ because the operating system actually is the one that writes out the core dump. And so a Linux core dump is actually simpler. I mean, they are actually similar enough in format. That's how TJ was able to get us to support debugging Linux core dumps on SmartOS because the formats are similar enough. But we have no desire in supporting. I mean, the support for post-mortem analysis is so weak in Linux in general. There's no real value to kind of emasculating our own core dumps for purposes of something that no one's going to debug with anyway. It's much more powerful to allow people to use our postmortem tools because you can use our postmortem tools from the zone. I mean, if you have native in your path, you can just run MDB on a core dump. So, well, I mean, it's like GDB basically, right? And they don't really have the same tradition of allowing arbitrary tools to run on core files that we do. So, I mean, we can run, if you take one of these core files, folks can see that it looks like, but I can run, P files on a core file. I can run PMap on a core file. I can do all these tools I can run on a core file. Actually, maybe that's a good kind of, let's actually just look at what a core file looks like. So let's take this core file that we got most recently, say from this PID 60. I feel like that's kind of a rarity to get such a low PID. What is a core file? It's an ELF object that is structured in a particular way that has a bunch of information in it. So we can use, let's use elf dump. I can use elf dump to actually dump out what this actually looks like. And I can use elf dump on a Linux generated core file as well, because elf dump, very powerful little utility to put in the toolbox. Elf dump just dumps out an elf object and potentially every section and so on. So this is showing us the elf header. This is an elf object, where it came from. It's of type ET core, so it's not an executable or a shared object. This is this OS ABI would be different if it were Linux. So there's a bunch of stuff in here, simple tables and so on. The thing that's actually most interesting is what's called the note section. And just the only thing I would make you aware of if you're ever debugging a core file, SmartOS core file, is the note section, because the note section has got a lot of kind of dead bodies and debuggers don't necessarily show you all of them. So if I dump the note section, this tells me this has got a bunch of in-kernel information that we copied into the core file. So like this is the PRPS info T. This is showing us what our argv pointer was, what our mv pointer was. And MDB probably should have a way to just give you all of this in a way that's kind of palatable, but it just doesn't, because this is such lower level information. There's the platform, the aux vector, PR status, so just everything that you would get from the PR status, why we died, the PR info. So we died on a segv. We had a map error, which means there was nothing here. You won't always see a map error. You can see there are other kinds of errors where you're getting seg faults because of permissions errors and so on. But in this case, it is a map error. And this is, if you're Patrick, this address immedately wakes you up. And hopefully we don't see vsyscall related problems from now on, but this address is a vsyscall address. So it's kind of a little bit of foreshadowing about what the actual problem is here. So let's see, just going down through this a little bit more, there are all the registers, there are the floating point registers. And then what you're going to get is the status for all the LWPs. Did I do it? No, it's one. And here's the FD info. There's the zone name, so we can see what the zone it was in. The FD info is telling us what the open file descriptors were. This is the way pfiles is able to work. And so you can see that stuff. There's LWPS info, so this is showing the LWPs. We don't have very many open file descriptors here. It's a relatively small core file. Okay, so that's elf dump. Let's actually use MDB, and that's totally neutral with respect to whether it's a SmartOS binary or an LX branded binary. Okay, I'm not actually sure why we get mappings not saved to these various addresses. That's probably something to be debugged there. But we've loaded a couple modules. Notice we've loaded the module libc.so.1. That is for the native libc. The MDB module for the native libc. We've also loaded a module for glibc. So we can see the actual, and I think actually in that case, we loaded the same module twice. We've loaded the MDB module twice. We saw the libc.so.6, and we think it's libc.so, even though libc is actually defined to be libc.so.1. So that's kind of a little bit of a bug, but it doesn't matter. Anyway, it just shows you there are two libcs in this process. And I'll use $M or colon mappings, which shows you this is you kind of first go to when you're looking at a core dump. It's like, all right, let's look at the address space here, and this kind of shows you the way LX branded zones work. We can see that up here, so we have the stack up here. The linker has a notion we're called link maps. link maps are denoted with this backtick. So anything that you see that has LMFD backtick on it, that is a native shared object. This other stuff are Linux shared objects. So we can see here's the native brand library, the native linker, SmartOS linker, and then that's pulling in where we actually put in the kernel as part of exec. Here is the Linux linker, and then the Linux linker pulls in, and then we've got our libc. So that this stuff is actually pulled in by the kernel. Then this guy pulls in our libc. So we've got our libc, the libc that's in every process. Then this guy pulls in the other parts of himself, and then he will pull in his libc, glibc, down here, among a bunch of other things. Yeah, that you just kind of know, but you can see to a certain degree based on the because we're going to allocate things this way, so you kind of know you do know that this is the order that things were mapped in the address space. Yeah, I mean you do know that libnss files, as a practical matter, was the last thing to be loaded. Okay, so that tells us kind of what the layout of the address space is. Yeah. Those are anonymous mappings. So this is where someone has either mapped dev0 explicitly, or this is part of in the shared object. It will indicate, I just need this much BSS, and the BSS the block started by symbol is just zeroed data. So if you do, if you have, if you've got global data in a shared object, that will be zeroed initially, and it will be in one of these. These are writable mappings. These mappings are.
Is that like
This is I mean this is usually the BSS that corresponds to the .so that pulled it in. So this is almost certainly his BSS. And that is probably this guy's BSS. And then you never know what the linker is doing. Is it's kind of pulling crap in. We can go actually figure out what it's doing. These are kind of small. Yeah, I was just going to say that that if you actually do a pmap on this guy, a pmap minus x will actually show you more. Never mind, pmap minus x will not work with core files. All right, we'll just do that on my shell process to show you. So this is just my shell. This is a native SmartOS in the global. Now showing you ld.so.1 versus the anon mappings versus heap versus stack. And you can see that the anon mappings are writable. In this case, writable and executable. That is presumably a PLIT, a procedural linkage table, which needs to be both writable and executable because it's going to jump through it. Okay, so did Robert have anything else that I should? Yeah. So if you run pmap, so there you're seeing that the actual anon is filled in, and pmap is actually giving you the permissions, which is useful. Colon mappings should probably be extended to do that as well. The asterisk also denotes that this is actually not here. It's not in the dump. And I'm not sure if that's because it might not have been touched. That might be the reason why it's not there. That's kind of an open question why these mappings aren't there. I should pull up a bit of the background so I can see what. There we go. Oh, red zones. There we go. Yeah. So so we don't expect them to be able to be there. But the asterisk denotes that the mapping is actually not present in the dump. Sometimes you will see a dump that has been if you kill -9 a process while it is dumping core, then we stop dumping core, and which I've got one has misgivings about because you don't have incomplete core files, but you have, and actually Zeller is part of the reason that we did this because Mike, you remember at Boxer, you guys had, it was taking days to dump core, and they would ultimately kill -9 it anyway. So if something is kill -9, you'll actually see when you pull up MDB, you'll see that I don't have these mappings because we were actually sig killed while doing this. But in this case, we got all the mappings we care about. So if we, to kind of get to the core of the question that Josh had, which is, how do I figure out what the hell happened? So the first thing to do is look at the stack, which is incredibly useful and tells us exactly what happened here. No, I'm kidding. In this case, and this is not uncommon where you look at a Linux dump in particular.
That's usually where I got to, and then
It's like, okay, well, yeah, right. Okay, and this is actually like the only. Oh, I was gonna say this is like the only case in like my career where you can actually look at the hex value of the stack and potentially know. And I'm convinced I'm gonna like forget this value. I've actually kind of thought about like having MDB kind of blare a klaxon when it sees this value because that would actually be kind of interesting if you could
just log it and just start tweeting it.
Yeah, exactly. If
don't you guys search for things on the internet and find it yourself doing it?
there's a couple of like Valgrind stuff.
So if you actually, there you go.
Yeah.
So this is like the only hex address you can ever Google meaningfully. Is this stupid? The Visa skull thing is just so ridiculously dumb. But whatever. So, but often stack traces are not useful. And often you're looking at a stack trace and it's often truncated. Actually, we'll come back to this one and let me go. I know we got core dumps from my. This is another problem I'm debugging. Or actually, this one's good. So this is much more typical. So this is you've got some amount of valuable stack, and then something, and then off into the ether. And what has happened here is Linux has the really regrettable property that it will reuse the frame pointer. So for very broken reasons, they've got this belief that you can make code much faster by reusing the frame pointer register and not actually using it as a frame pointer. This was barely true on x86. x86 was register start, that was true. And you could probably construct examples that were micro-optimized where that might make a difference. It is definitely not true on AMD64. Like, there's really no reason to not store a frame pointer. And what it means when you don't, because it's just a register movement, and when you don't store a frame pointer, it means like you don't have a stack. So it's actually it's fucking impossible to debug. So that's one thing. If you actually compile on SmartOS with GCC and tell it to emit the frame pointer, we ignore it. And we put the frame pointer in anyway because you don't mean that. But unfortunately, it has just crept in and kind of like become the default option in a lot of places.
How many general purpose registers are there for programs on
there are a lot more. So you've got a lot more registers, and you also just the reality is that if you are a function and you're gonna call other functions, which functions often do, if you are a non-leaf function, you got things that are going to go to the stack no matter what. So the idea that like you're going to somehow by reusing the frame pointer, you're actually going to save yourself a trip to memory to store something to the stack is like it's almost certainly not the case. Which is part of the reason why you're gonna have to put a bunch of your stack down onto the state. You bunch of state down to the stack when you make a call anyway. Yes, we'll get to. There we go. FNOM frame pointer for life, indeed. Unfortunately, it's a little long to get tattooed on the knuckles. Okay, so let's see a couple of things. So this is what the stack will often look like. If you want to get a better feel for the stack, so we have this part of the stack because this is the stuff where we actually save the frame pointers. So if you actually like look at emulate, that is saving the frame pointer. This is what it is this 2-byte 2 instruction sequence that is ridiculously optimized in the microprocessor that you are quote unquote saving. When we're not saving the frame pointer. So, but that is the sequence that saves the frame pointer. That's why we can actually see what happened through here, but we can't see beyond that. What I often do is just take the stack pointer or base pointer if the stack pointer is corrupt, and we'll talk about that in a second. And I just, so the comma syntax in MDB says repeat the following command. Recall that we are on a, addresses are the kind of the fundamental primitives, and inspecting values are kind of the fundamental verbs. So in MDB, the / is a verb that says I want to look at what's here. Capital X says I want to see this as a 32-bit hex value. Capital K says this is a 64-bit hex value. And you can actually run : formats. Will tell you all of the formats. If you do /p, it says if you use the P format, the P format is here. I want to look at this as a symbol. What I do is I look at dot as the symbol plus offset, and then I like a new line in there. So what I do is comma, let's say 1,000, some number, /nap. And so that's going to be new line, and then I want to basically see this symbolically. And this is just going to walk up my stack, showing me until you see no mapping for address. That means you hit the top of the stack. Do not need to do 1,000 there. We'll get done less than that, for sure. Okay, so this is the whole stack up until the point where we run off the end. And you can see, actually, it's like, oh, well, what's that hanging out at the top of the stack? And that is actually usually the environment. And I'll do : dump to see at the top of the stack. Usually these are the things that usually the kernel stops at the top of the stack for you. As we look up the stack, because the reality is that you do actually have to keep track of where you came from. And you have to keep track of your state. This is part of the reason why not saving the frame pointer is such a fucking lie, because it does have to be stored somewhere. But now instead of, you just haven't stored it
in a register, it's on stack.
Instead of like in the conventional register where everything goes to look for it, you've squirreled it away somewhere else that we don't know where to find it. So if you look up here, what you will see is so let's see, there's, you will usually see the frames. So we can see, for example, that we're actually in, it looks to be F access at, we can begin to see kind of where we are, which can be, now it's a little bit like you're kind of going through the trash here trying to figure out stack traces, and it's definitely annoying, but you do actually have the information on the stack about where this thing came from and why.
So that I put the thing with the symbol is what
is it? That's an instruction pointer.
That's the instruction pointer, and then the things below that are the.
Well, this is just what's on the stack, and what you're looking at is like, well, if something's an instruction pointer that's sitting on the stack, it's like it's probably a call site.
Right. Okay.
And there's
so everything else is just like there are no symbols for this.
Other stuff. There's no symbols for this. We don't know what that is. Now, in some cases, you'll see that a lot of these addresses are going to actually, like that address is a pointer back onto the stack. So that is either part of a frame, or it is just it's a pointer to a value that was on the stack.
You just know that because it has the same.
It's in the same range.
It's in the same range.
And sometimes, and actually the other thing, what is so annoying about so disappointing about Linux is that in particular, the things that omit the frame pointer are the libraries. So sometimes you will have things where one object was compiled with frame pointers, it's calling through a shared object that has no frame pointers, and then it's calling into us, and you can actually find a stack on the other side of that shared object. So that by calling through that shared object, you got no idea where it came from. But if you can get to the other side, and actually it might even be true here.
Get to the other side when reading through this.
Yeah, exactly. And you can see sometimes, I mean, you can begin to, in this case, it looks like it's omitted here as well. Because you can see, and what I'm looking at, by the way, is, okay, libvmtools.so, host info demonize plus 170. Let's go look at that. So you can see that's a call site. right? And that's a return address for a call site. So that called host info reset process state. And if we look up here, let's see if we can, I'm just kind of looking for other things that are, when here we can see that we are through LX unsupported, which is definitely interesting. And actually to the point where, let's actually look at that string. Like, unimplemented system call 172, no equivalent Solaris functionality. Like, definitely relevant for this problem, right? And what has happened, and actually this is one I need to get a bug filed on. This is something that kind of ends up dying. We just need to get this fixed. This thing is getting an enosys on an IOPL, and it's not expecting enosys, and then it's core dumping because of that.
Where was that address from?
I got that on the stack because what I saw was the LX unsupported in the stack, and then I saw what is clearly string data, right? And so what I did is I just took that address and just then dump that out. I could actually also just do /s, look at that as a string, but it may or may not be relevant to the problem, but it's like, okay, you know that this, like, you're going through what they had for dinner recently, and you're like, okay, like they definitely they ate a quarter. That might be relevant to they pooped out a quarter, whether that's relevant to the problem or not. That is, and like sometimes you'll see a well-formed stack through here. We're definitely not seeing it here, but every once in a while you'll see it. And actually, that looks almost well-formed, but it's not. So you can actually pass addresses to stack. Hey, Kevin. So that's a good way to kind of figure out where you might have been, what you've been going through recently. Let's go back to the actual core file in question, because this was, and unfortunately, it's kind of the nature of some of the core files that you've had in particular are really, really nasty because they are dying super early. That one is not. This one is actually not dying that early.
Yeah.
But like when we were finding. When it's not even getting through exec, you've got a core file that is really hard to make sense of. So some of these are going to be just hard. But yeah, when we were finding because when we die deep in exec, so we've created yourself, right? You fork, so you're in the process, you're execing. We are past the point of no return with exec, so the old address space is gone, and now we're putting together the new address space, and we're getting ready to jump into user land to have it go do dynamic linking. And some of the problems that Josh has had, it's like something breaks halfway along there, and we're just like, fuck. So what we do at that point, I mean, you get a core dump at that point. You get a core dump of something that literally didn't even execute a single instruction. So you go to look at the core dump, and you'll see like the registers will be zeroed. Like there are no registers, which indicates, and actually in some ways, if you're looking at a core dump that's that insane, kind of the first place to go is like, okay, I've got exec failure here. And if it's reproducible, then you're going to go down the dtrace route and figure out where exactly is exec failing. And in that case, exec was failing because we were hard coding the interpreter. So let's go back to these guys, and let's take that little bash 60, because this is the problem that kind of is motivating this. And the first thing to do is $R or regs, tab complete that, : regs. So this shows you what the registers were. And in particular, you want to know the instruction on which you died. And normally this will tell you, like, okay, what did we do? Like, did we reference a null pointer here? Did we? In this case, you're like, okay, well, what did we do? Dis that. It's like, oh, there's no mapping for the address there. It's like, oh, okay, we are in space. So often these problems are really, really hard because you have jumped into space. And depending on how much you fucked yourself before jumping into space, it can be very hard to figure out where or why you jumped into space. In this case, so the next thing we go do is like, all right, what does the actual stack pointer look like? And we know that's useless. But let's do the :100 nap thing, and we see at the top of the stack is libc.1 time plus d, and if we disassemble that, we see this is where you're kind of like, welcome to Linux. Like, why are we in space? Because we moved space into a register and then called through it. It's like, Well, that explains that. I mean, we literally took value, crazy fucking value, that is definitely not mapped, loaded into RAX, and called through it. Case closed. Exactly. So, because he put the shotgun into his mouth and then pulled the trigger. And this, and as we've kind of been alluding to,
That's a V.
this is a vsyscall address. This is the magic stupid vsyscall page, and this is this dumbass thing where they were going to make virtual system calls and implement this in.
I thought that was deprecated.
It is deprecated.
So
It is.
still in use?
Because you've got this in particular. So no, I mean this problem only occurred on Nginx, and that thing's I don't even know what.
Really old guy.
Yeah, it's pointless.
Debian 7 is what the image is based off of, but I don't know. I don't know anything about what they installed. I didn't look at the package list yet.
And the choice to use vsyscall for this is all about the compiler access. Is it?
The vsyscall thing is that's going to be that's a glibc-ism, and they eliminated vsyscall with VDSO. There we go. Yeah, Patrick is so it used a different libc, and
They're not so that. Okay.
and I don't know if it's either old or if it's eglibc. I think it does that.
eglibc we saw I think doing that, and then there's a few different libcs you can install. So.
Yeah, unfortunately, this is a construct that existed that
eglibc, that's the old EGCS.
that's an embedded glibc. It's unfortunately, and it's like a lot of things in Linux, where it's like it's a stupid wart that existed for a short period of time, relatively speaking, but now these things are out there. So this case, you're like, oh, okay, this is the stupid vsyscall thing, and this in this particular case, what actually happened is that the way Patrick implemented this, which works very well actually, is we don't actually map the vsyscall page. We pick up the segfault handler, and so if you segfault on the vsyscall address, we know what's going on, and we clean it up for you. We give you what you want. We know what system call you're trying to execute. There are only 4 of them, and we basically execute that for you, give you the result, and then you return the signal. And what happened here, 3 of them. Thank you, Patrick. What happened in this particular case is due to a really nasty bug. The segfault handler was restored to the default disposition, and the default disposition of the segfault handler is to kill the process. So we did not execute this is part of the reason why something of the smoking gun is in the LX debug output. We never saw us come in to the LX branded stuff, and the reason for that is because the signal mask was incorrectly set because of this other bug. Yes, yeah, which totally not Patrick's fault. This is definitely a very weird. It's a libc-ism. So anyway, but that's a pain in the ass. But what you can tell, at least from the top, is like, okay, this is what actually happened. And I think Conqual and Status will tell you you've got a segfault because you went to this address. And I think if we does psig work on.
So you should never see
No.
segfault with that address because that should always be handled. By
Yes. We should never see a segfault with this address. If we see a segfault with this address, in fact, one thing to note, then the vsyscall mechanism has failed.
Right.
I actually do. In fact, Patrick, one of the things I want to follow up with you is actually on that. We need to make sure that when you set the sigmask for a signal handler that masks out segv in that handler, that we will still take the segv if you hit the vsyscall. I actually think we already will, but we just need to go verify that. But if there is another bug in that where we, for whatever reason, wiggle into the default disposition for segv, then this is what will happen. We'll die with that address. One thing to know about the Linux address space is that, and I'll just debug my shell process there to give you kind of a contrast. Actually, let me find ZoneADMD being my token 64-bit process on a system. Something. Oh, I'm already inserting that. Actually, I know what that's about. So this I just grabbed a Zone 80 MD. If you look at the mapping for a 64-bit process on us, you'll note that the addresses are all very high, much higher than for Linux. Linux is just in the way they did it. It's not necessarily not totally stupid, but it's just the way they did it. They start their mappings right below what's called the VA hole. So we don't actually 64-bit microprocessors don't actually implement the full 64-bit address space because you don't need to. Turns out that's really, really, really big, and those lines are actually really expensive. So there's a virtual address hole where you can't actually map anything, and it's and whenever this is drawn schematically, it's always drawn into usually like thirds. You've got the third of low addresses that you can map, the third of high addresses that you can map, and then the third that is the VA hole. But if it was actually driven to scale, the address space is 99.9999% VA hole, right? Because that's the way the whole powers of two work. So when you take a bunch of address lines and hard code them, you actually eliminate most of the address space. But it's not a problem. It ends up being what 48-bit on but this is basically your highest address on AMD 64 that is below the VA hole. For us, we put things above the VA hole, and the heap is below the VA hole on a 64-bit binary on SmartOS. Linux actually, it turns out this is the HHVM bug. HHVM actually depends for sure implicitly on the fact that on 64-bit Linux, everything is below the VA hole because it's actually depending on negative 64-bit numbers being a token and not a valid pointer. So that's why HHVM blew up in a very weird way on us. These are the kinds of problems. This is the way that Patrick and Jerry and Josh and I spend our lives.
This can never be a valid address.
Yeah, exactly. That's right. You'll see that the address space layout is just different on us. So one of the things that as you're going to kind of debug this stuff, and let's actually go back to that other binary, the other dump. So what if you actually want to use, actually go debug it, and we've died in the let's take this guy. And let us, if we want to actually look at some of the LX structures, let's say. So if I : print and I go to tab complete, there's nothing here. And there's nothing here for something we will absolutely fix and should fix. There's nothing here because we're actually we're in the global. And we actually don't know where I think this is why it's failing. Actually, I shouldn't say this for sure. The fact that these are native binaries are tripping us up, put it that way. And we're not finding, hey, Orlando, we're not finding the CTF for, say, the LX brand stuff. And this is where we get into work that Robert did actually a little while ago that's super, 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 super valuable. And that's called typedef. So there's this command typedef, and you can : help typedef. There are two ways to know that Robert has written something in MDB. One is that the help message is really complete and thorough. So there's a really complete help message. If you're reading this and you're thinking like, God, I think this is probably Robert because this help message is so thorough and I've got like little bullet points here, and like I've got ASCII art bullet points. And there don't seem to be any kind of like acidic remarks about other systems, so it doesn't seem like it's Brian. But Keith, exactly. Like it seems to be remarkably devoid of anger. And then you look at the examples, and it's like, and that's Robert. It's like, all right, we got some Frodo, we got some Gandalf. So fortunately, no Elfin. I am waiting to like get the actual like Elfin in one of these things. Have my terminal like start core dumping or whatever. So : typedef is really useful. And the thing that I kind of originally thought of it, in terms of what Robert originally did, and what I kind of like was where it was stuck in my mind was the ability to define these types manually. So you're looking at a system, and this is where, I mean, you got to be deep into a nasty problem where you're starting to infer structure offsets on something you either don't have source code to or what have you. You can declare a C type that has that, and then start using : print to print it out, and : walk, and so on. So that's helpful. But actually, there's something that's much more kind of broadly useful. That this is useful for sure, but you've got to be kind of deep into a really nasty problem. What is much more broadly useful is the ability to say, hey, I've got a binary, an alpha object over here that has CTF information that I want. Like, just never mind whether you think it's relevant to me or not. Like, I want the CTF information to be loaded into my debugger. So I want you to grab this thing, slurp it in, and I want those types. So what that allows us to do is do exactly. And then you can, in this case, you're kind of getting around the fact that, and actually, so we need to go debug it. I mean, for whatever reason, MDB is getting tripped up. This has been there. I definitely felt like I only discovered this when I think Robert and I were debugging a problem together, and he's like, well, why don't you type that -R? And I'm like, the what now? Excuse me. And when we actually, and then we pulled in, because when you're debugging a failure it's annoying that we don't have CTF in the LX brand zones, but we actually do because we can pull it in. So I can do user lib AMD64, AMD64 lxbrand.so.1. So it came in April of 2013. Well, that was recent. But I mean, I think right. There was a famous trade of that Robert got Josh to do some work that he wanted done that he didn't want to do, and vice versa. And Robert's work was much easier than Josh's work. But now, and the other work that Robert did earlier was tab completion, which is really useful. So if I just : tab complete, print and tab complete, I can now see all the types that pulled in. So that has pulled in a bunch of super useful types. So if I do like struct LX, I can see these are all, and if you're debugging an LX problem, I mean, being able to look at the, for example, the LXU context, like that's really useful. And being able to not have to actually like count offsets, but being able to find where things are. It's also super useful if we find the, let's do : type def -R. Let's see if, not sure why if that conflicted. Yeah, I'm not sure. That failed to add types. I'm not sure what, but we can't argue with Prometheus too much. We got, anyway, I can also pull in libc, and that allows me to print out like the ULWP structure. So now I can walk the ULWP. Those are my LWPs, and print ULWPT, which has the user level snapshot of LWP state, which can be really, 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 really useful. So actually, if we go back now to the other problem, what was the if we go back to this guy and debug him, and then we can type def -R, and let's pull in libc.so.1, and then walk ULWP. This should take you to what the actual problem is here. Print the ULWPT. We can see the UL sigmask, which is what it is storing as the sigmask. This is where we have the value that's wrong. So, but we can see what its values are, which is really important if you're debugging that kind of a problem. Yeah, and then I can also I can also tab complete that. I can and print it like that. So very useful stuff. Tab completion, very, very, very useful. So that's I would say that's the kind of the whirlwind overview of debugging LX. most of our I would say that in terms of the way we debug a lot of these problems, hopefully we haven't had too much stuff of just like, I just have a core dump from a process that didn't work. That's going to happen more when we go live. And it's going to become harder because we're going to hope that those are reproducible. Because it becomes really painful to just debug from a core dump. But there's presumably going to be plenty of that as well. That VM tools is an example we can debug it just from a core dump. But this is the way we're going to be kind of debugging that going forward. And then I would say using dtrace, and then a lot of MDB and stopping MDB and kind of stepping through things that way. So Patrick or Robert or Josh, are the things that kind of big things I'm missing here? Yeah, exactly. I think that's right, Robert. Robert is speculating on what the actual bug is on why we can't find the CTF. We need to get Robert on. I would get Robert on a plane or train, but we do have this whole like VXLAN work to do, which is probably important. Yes, and so this is what we do a lot, what TJ is referring to here, where we, and especially the LX debug, you put a predicate in place. You use stir to put a predicate in place on LX debug. When I see output that looks like this, I want to stop. And then you can stop the process, and you can G-core it, you can attach the bugger to it, what have you. So we do that a lot with these problems, and using kind of MDB and dtrace back and forth. So any questions on them? This is helpful? I'll unmute these guys here. Yeah, Patrick, sorry about that. I should have assumed that, like, wow, I must be the last person to know about : type def -r with respect to LX debugging, but that was obviously not the case. So sorry for any waste of time that you had as well. It's a real lifesaver for LX. Yeah. No, so what that is doing is that's saying, and you can do it for Bunyan as well, right? Where you're saying, I got a string from a Bunyan probe that I've turned on, from an LX probe that I've turned on. I've got the string of like when I know the bad thing is happening or starting to happen, and I use stir to match that string and the predicate, and then I take the action to stop the process. Yeah, sure.
So there's an argument.
Yeah. There's an argument to stir. So yeah. So let's assume that that when I saw syscall 12 refactoring the LX kernel for break, like that is when the shit hit the fan. So let's assume that was the problem. So then I could do this. So dtrace -n, LX star debug.
Just gave it to you. They're all racing to give you. Keeners.
It's total keeners.
I see. Okay.
Actually, I don't like that, so I'm not doing that one.
Stir is in
What's that? Exactly. And so stir, copy instir arg0. That was stupid. That was actually that's very unlikely to be in that string. Possible, but very unlikely. And yeah, let's just get vectoring there. So if that does not equal null, then stop. Then say trace did stop. And if I just run that as is, it's going to complain for two reasons. One, we're not matching any probes, so I need -z there. And then it will still not allow me to do it because it's like, hey, you need destructive actions. So that's where I need the -w. So now, okay, we're good to go. And now if I do LX dtrace +1 bash, okay, now I can see this guy has just stopped. And he's stopped now, and I've got this process. Oh, you can definitely, yes, you can absolutely really fuck with people. And now I can attach to the debugger, and I can see exactly where I am when I actually called that, right? So we can see, there we go. So if that were it, exactly, this is how we can absolutely fuck with NPM. I do think we should, and actually it is really one thing you can do that is extremely annoying. It's why it's a destructive action. I mean, we can make it so whenever a, I mean, you could, for example, have something that whenever if you wanted to fuck with someone, have very elaborate predicates and then stops them on their first system call and just stops them and leaves them there, they will quickly flood themselves with stop processes. It's going to be very hard to figure out what's going on. Anyway, so that explain that, Rob?
Yes.
Cool. Other questions? Or this is what you're.
Yeah, definitely.
Cool. Anything else online, guys? Cool. All right. Well, hopefully this helps. And if there are other things that are, I mean, I would say adding debugging support for LX is really, really helpful. So I think we will fix that CTF issue at some point. But if there are other things that, if you're stuck on an LX bug, you can always spend time actually adding debugging support. Actually, Patrick there's a really good example from Patrick where he was debugging a still actually undebugged nasty memory corruption problem that might not even be an LX problem, which is the other thing that's going to be a challenge here, where you got programs that are dying that have nothing to do with LX, right? They're dying because they have a bug. But one of the things that he was hypothesizing is that the TSD was being screwed up. So we weren't properly saving, Patrick, we weren't properly saving FS base in the core dumps, right? But he basically made it so we would get that information out of a core dump, which is a good way to kind of make forward progress when we're stuck. Right, because FS-base was switched. So actually getting both the native FS-base and the branded FS-base in the core dump and actually we should probably add a lot more branded stuff in the core dump. There should probably be a branded hook where we're dumping lots and lots of branded state in core dumps. Anyway, so okay, well, nothing else. Thanks everyone. So I'm going to stop the recording.